I think that was homework 7 or something. Yeah. So let's start with some questions there. If you guys have any questions from homework 7, bless you. You're welcome. We'll start with those, and then we'll do another little timed factoring practice as become kind of our standard procedure here. And then we'll continue talking about solving a little bit and kind of complete that topic. And that'll probably be it for the day. Okie dokie. It's a big completion, though. We got a lot of stuff to do to kind of wrap that up, but that's the plan. But right now, we're looking at work 7 and looking for questions from that anybody might have had about any of the questions from homework 7. I'm happy to answer whatever, whenever, whoever, however, if ever you have questions. Megan. Number 5. Happily. Oh my goodness. Well, no wonder you were confused on that. Look at the typo there. Those y's are not supposed to be in the exponent. Goodness gracious. That's what I get for not proofreading what I typed out, huh? So this should be 33x squared y, and this should be 3x squared y, like that, where the y's are not in the exponent, but it's just another variable. That probably makes it a little more obvious what to do then, huh, Megan? Well, let's finish this one anyways, just in case, since obviously you probably got stuck looking at it from the weird location of the variable. Like, that's not even a polynomial. You got a variable in the exponent, you doofus. So we'll start by moving everything onto one side. So we'll subtract 3x squared y. Move it over there. And we'll subtract 6xy. To do that. And then we'll add 6y. To do that. And now we're equal to 0. Remember, the instructions for these problems were to solve by factoring on these first 5, so we got to get it equal to 0 as our very first step. Now I notice that I have a greatest common factor amongst all of these. There's a common factor of 2y. So I'm going to start by factoring that off. To there. Megan? Oh, sorry, -2. Sure. Thank you. Nope. Good point. Thank you. Appreciate it. Again, feel free to interrupt in those situations before I get going too far. If you see it or you think there's a mistake, let me finish the whole problem and be like, I think that was supposed to be a positive, or, like, well, now we got a million things to fix to go back and make this right. As soon as you see something that you think is wrong, I encourage you, please speak up. I make mistakes. It's okay. Okay. From here now, I can factor. I'm looking for the two things that multiply to give me 15 times -1, so -15, and add to give me 2. Hopefully, it's easy to see that would be 5 and -3. So I'm going to rewrite this as 15x squared plus 5x plus -3x minus 1. I'll make my two groups. From the first group, I can take out a 5x. Oops. And then from the second group, I can take out a -1. And I notice each of those have a 3x plus 1 in common. So when I factor that out, I get here. So far, so good. And now we can apply the zero product property. So I can take 2y and set it equal to 0, 3x plus 1 and set it equal to 0, and 5x minus 1 set it equal to 0. If I divide both sides by 2, I get just that 0. If I subtract 1 and divide by 3, I get negative 1/3. And then if I add 1 by 5, I get positive 1/5. So those should be my 3 solutions for that one.
Mr. Kulik,
Yes, sir.
could you do number 9, please?
Yeah, no problem. I'm going to
Thank
pause here for a minute because I still see people writing things down, but that's okay. We'll get to number 9 next.
All right.
No problem. No problem. I'm just kind of narrating since you guys can't see what's going on in, in my room, and some of the people in the room can't see or probably couldn't figure out what the heck is he waiting for. That's all I'm waiting for. All right. So we look good here. So we'll go down to number 9. Okay. So here on these problems, we're asked to use the reverse order of operations. So the first thing I want to do is undo any addition or subtraction going on. So I'll start by adding that to both sides. Now I can't also subtract the 3 because that's inside the parentheses. In order for me to get at that, I have to clear the parentheses out of there first. But to clear the parentheses out of there, I got to get rid of the coefficient of 9 and get rid of the squared. So it's going to be a minute before I can get to that, but that's okay. Next thing I need to undo is multiplication or division. So I have a times 9 here on the outside, so we'll divide both sides by 9. And then to get rid of the squared, we'll square root both sides. Now the square root cancels the squared. Because I square root both sides of the equation, I create a plus or minus. And then because we're square rooting a fraction, I can do the square root of the top over the square root of the bottom. And I notice the square root of 4 is just 2, and the square root of 9 is just 3. So let's simplify that down to just plus or minus 2/3. And then the last thing is to just subtract that 3 over. So I have negative 3 plus or minus 2/3. Now we can get this, so I can do negative 3 plus 2/3. To add those, we need to make a common denominator of 3. So negative 3 becomes negative 1/3. And when I add those fractions, I get negative 7/3. And since it's a plus or minus, I also have to do negative 3 minus 2/3. We'll make that same common denominator. And negative 9 minus 2 is negative 11. So these are my 2 answers there. Joe, is that okay with you?
Yes, thank you.
Yeah, no problem. Who else has some questions from this sheet? I'm happy to do some more. Elizabeth. I have to hesitate every time because I almost call you Caitlin probably every single time I look at you. 12, certainly. Okay. So here we're asked to use the quadratic formula. So I'm going to start by just making sure that it's equal to 0, which it is. And then I'm going to identify B and C. and then plug those into the quadratic formula. So x is equal to negative b plus or minus b squared minus 4ac all over 2 times a. And now I'm just going to do some simplifying. So negative of negative 11 is positive 11. 11 squared is 121. 2 times 4 is 8, and 8 times negative 21 is negative 168, but it's minus a negative, so it's really plus 168. That's over 4. And then 121 and 168 is 279. And I wonder if 279 is a perfect square or not. That's rather a suspicious looking number to me. Nope, it's not. So the next thing I would think is, okay, can I simplify that at all? Well, let's check. The easiest way to do that is to just kind of do a prime factorization of 269 or 279. So I see that's definitely divisible by 3. 3 and 93. And 93 is divisible by 3. That's 3 and 31. So I can really think of 279 as 9 times 31. Megan. Oh, 289. Oh, good. Thank you. That's even better. You can ignore all that mumbo jumbo, because that's an even better result, because the square root of 89 we can do. If I type that into my calculator, the square root of 289 is 17. So 11 plus 17 over 4 is 28 over 4, which is 7. And 11 minus over 4 is negative 6 over 4, or negative 3 over 2. So those are my two answers. No problem. Walter, I saw your hand up.
Yeah, I was going to ask for 11.
Sure. Yeah, we can definitely do 11. That's the one right before this one, right?
Yeah.
Okay. I just had scrolled over so far I couldn't remember what number we were looking at, but happy to do 11. Those of you still writing down 12, is it okay for me to move? Okay. Again, if you need to go back and look at things, it's okay. This is all on OneNote, right? So A is 1, B is 1, and C is negative 20. You good with that? So we'll plug these in. So x is equal to negative of b or minus b squared minus 4 times a times c all over 2 times a. So that's negative 1 plus or minus 1 squared is 1. 4 times 1 is 4 times negative 20 is negative 80. But we're minus a negative, so that's really plus. 1 plus 81 is, or 1 plus 80 is 81. And the square root of 81 is 9. So negative 1 plus 9 over 2 is 8 over 2. And negative 1 minus 9 over 2 is negative 10 over 2, which is negative 5. Okay with that? Yeah, of course. Yeah, Elizabeth.
What if like the numbers like are if we don't add up, like, it's like 7, and like, use like 2 to some numbers.
It's like 7, like the square root of 7?
We had like 279, and we trying to figure out the numbers, like,
So you could have an answer where we just leave the square roots in it, and that's okay. So for example, if we had like, let's take a real basic example like this one. So A is 1, B is 1, and C is -1. So that's going to give me -1 plus or minus. 1 minus a -4 is 5. And that's like all you can do. And you could leave an answer like that. That's perfectly fine. We'd prefer to leave our answers with the square roots in them rather than making them into decimals. You could certainly make that into decimals if you wanted to, but I would ask you not to do that. Let's just leave our answers with the radicals in it. This is called an exact answer. Now, if I wanted to, I could take my calculator and like type that stuff in. I could do -1 plus the square root of 5, and then I could divide that answer by 2. And one of these, or that one, would be 0.61803398887. And then I could do the same thing except subtracting the square root of 5, and that's going to give me -1.168. These are approximate because those answers keep on going, like the decimal never ends. We've rounded at some point wherever we decide to stop. This is exact. Typically, we prefer the exact answers. If you're given a multiple choice test or something, like on the ACT, typically their answers be represented as exact values like this. So it's really quite helpful that you're able to kind of give an exact answer. And that's really what I'm looking for more often than not in a class like this. Yeah, that's a great question, though. Again, we're pretty early in the solving steps here. We'll spend quite a bit more time here. This is, again, a very important skill from this chapter. Probably the second most important skill right after factoring is to be able to solve these quadratics. So we will spend quite a bit more time there as well. Okay. Anybody else with questions from this homework before we move on to the next thing? Megan? 13? Okay. So A is 2, B is 1. So -b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So I have -1 plus or minus 1 squared is just 1. 4 times 2 is 8. 8 times -11 is -88, but it's really plus. So that's -1 plus or minus the square root of 89 over 4. I can try to simplify the square root of 89, but I believe it's prime. I think so. Yeah, I think that's prime. So I don't think there's any simplifying we can do. So this guy would just end up being our final answer. And it's maybe easier than we thought it was going to be, right? Because there's nothing left to do with the square root of 89 to make it any simpler. So yeah, we're just kind of stuck there. But that's okay. Okay, so we're going to do another factoring practice now, and then we'll start, or we'll continue talking about solving, because there's one big hole still in our solving situation that we haven't addressed yet that I've intentionally avoided. You probably haven't noticed that I've been avoiding it, but I have been. And we'll tell you what that is in a moment. So I'm going to pass out these factoring practices. Just leave it face down on your desk. I'll tell you to do so. This factoring practice is going to include things that you can do with the shortcut, things that you can't do with the shortcut that you have to do the full long factoring method on. And then there's going to be things on here that maybe you can't factor at all. So you have to be careful. We'll give a little bit more time to do this one as the factoring is a little bit, a little bit more ambiguous and maybe a little bit more difficult because, well, there's some that take a little bit longer, the ones that you have to do the full method on. And then there's ones where maybe it's not totally obvious whether you can even do it or not. Which again, take a minute to kind of make sure that you can do it or not. Absolutely. You're welcome. You're welcome. So again, we'll leave that face down until I tell you to do something with it. But we'll do a full 5 on this. Again, these are getting a little bit harder, so should be giving you a little bit more time. Those of you guys that are doing this from home, I'm going to drop the practice here into the content library right now that we're doing. Again, if you takes a minute for your computer to catch up and get synced and to find the sheet, don't worry about doing this at the exact same time we are. Just time yourself for 5 minutes and get it done and see how you do. If you get a chance to get it and get it synced and you're ready to go with us, that's not a big deal. If you're a few minutes behind, whatever, you guys all have your cell phone probably sitting right next to you. You can time yourself pretty easily. Just do the best job you can. It's not a big deal if you don't get it exactly in there. It's not exactly 5 minutes or whatever the world. Again, this is not really an assignment. It's just for practice to help us get more comfortable with this very important skill. So I've dropped that into the content library now, and I just forced my notebook to sync. So those of you at home, if you check here, you should see that kind of popping up into your content library. You might need to do a sync also, but that should be popping in here in the next minute or so. We're going to start, though, here in class. Again, if you're a minute or two behind, no big deal. Just time yourself. It's 5 minutes that we're doing. On your marks, get set. Factor. About halfway. And a pencil down. Woo. Okay. Quick show of hands on completion check. At least 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, good. So again, this was quite a bit more difficult than some of the previous ones, but we're still doing about the same number of questions, it seems like, on average, which is good. Let's run through the correct solutions here, and you guys can check your own. Again, no penalty for right or wrong, just kind of be honest on how we did. And as always, the order in which the two parentheses appear does not matter. Oh my goodness, I put the same one on there twice. Mr. Kulik, you're so silly. Yeah. So there's the solutions. If anybody needs me to scroll back up, holler at me and let me know. We can always scroll back up here in a minute. But usually, by the speed that I write them down, you guys are pretty decent with getting things checked and copied if you need it. No problem. Okay, has everybody got a chance to check theirs? We're good? Okay, correctness check. At least one correct. At least 2, 3, 4, 5, 6, 7, 8, 9, 10. Good. So in general, it seems like the ones that we're finishing are basically all correct. So it seems like maybe you missed 1 or 2, but by and large, you're getting these correct, which is excellent. So that's good. Everybody's feels okay? Good, 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 good. So we'll return back to solving here. So we're going to kind of pick up the notes now. So I've warned you guys, it seemed like last time we were done with solving, like we had completed this, we could now kind of solve anything, regardless of the situation. That was almost true. There is still one thing that's kind of going to cause a little bit of a problem for us. And they're going to be situations like this. And you're probably saying to yourself, yo, Mr. Kulik, we did situations like this yesterday or Wednesday. This isn't a big deal. Like, I know exactly what to do here. I'm just going to subtract 1 from both sides. And then we'll square root both sides. So I have x is equal to plus or minus square root of negative 1. Does anybody see a problem with what we've written there? Megan? So, yeah, up until this point, you've been told you cannot take the square root of a negative number, right? And in a way, that's true. The square root of a negative is not a real number. But we've run into a situation like this many times in our mathematics education to this point, right? When you're in elementary school and you learn subtraction, and you did like 3 minus 5, all of a sudden you got a new kind of number that you'd never gotten before, right? Like this negative number. So we had to like define a new set of numbers in order to be able to do this kind of subtraction. Or later on in elementary school when you started doing division, and you did something like 3 divided by 2. You got a new kind of number. You got this fraction or a decimal that you'd never gotten before. So we had to define like a new kind of numbers to be able to do this operation. We're going to do the same thing here. We're going to define a new kind of number so that we're able to take square roots of some of these negative values. Okay? And it feels like you're just making stuff up now, but we're not. This is something we've done kind of over and over and over again so we can continue doing more complicated things. So this is not a new thing that I'm doing or just making up. And remember here, when I say real number, I'm not talking about like it's concrete. I'm talking about those sets of numbers we talked about there in the first few weeks of school, like the integers and the rational numbers and the real numbers are a class of numbers. Right? The real numbers were anything you could represent as a decimal. So anything at all up until this point was considered a real number. What we're going to do today is we're going to define a new set of numbers called the complex numbers. So the complex numbers are defined as things in the form a plus bi, where a and b are real numbers, and I we're going to call the imaginary number, where I is going to equal the square root of -1. So up before, if we return to our previous example, where we had x is equal to plus or minus the square root of -1, this didn't have an answer before, but now after this new definition, we can just say that that is equal to plus or minus I. So before we go and circle back into solving, we've introduced this new set of numbers. We should probably talk about like making sure we can identify when we're looking at a complex number or not. We should talk about how we add, subtract, multiply, divide, do the exponents or absolute values or whatever on these things. Just to get a little bit more comfort dealing with these complex numbers. And then we'll kind of circle back and incorporate this into solving. Okay? All right. So we're just taking like a little detour away from solving because we've introduced this new set of numbers that we need in order to solve everything, all these quadratics that are possible. But since we've introduced this new set of numbers, we need to get familiar with them, right? So let's just do decide whether something's a complex number, and then we're going to give the values for a and b. So let's say we have 6 minus 5i. Is this a complex number? Yeah, right? What's the value for A? 6. What's the value for B? -5. Everybody's okay there? Of course. Yeah, go ahead, Jacob. Is this a complex number? Yes, we would just need to think about it as like that way, but we can write that as a complex number still. Everybody's okay with what we did there? We just took that common denominator and broke it into two separate fractions. Okay, so what's the value for A then? 3/5. And the value for B is -4/5. Yes. Got to take those negative signs with them. Everybody okay there? How about 7i? Yes. Yeah, so we can think about this as 0 plus 7i. Yes. So the A is 0 and the B is 7. Okay. Yes. This is a complex number still. How? Well, I can think about it as 6 plus 0i, right? So sneaky. So the A is 6 and the B is 0. So what is this basically saying to us at this point? All numbers are complex numbers. Exactly right. So everything that we've encountered before gets included in the complex numbers. plus some stuff we had never seen before, right? So it's just extending what we had before, which is always what we did, right? When we had started with positive numbers, we extended the positive numbers to include negative numbers. When we ran into fractions, we extended the positive and negative whole numbers to include fractions. Then we extended that to include things that couldn't be represented as fractions. And then we extended this again to include these imaginary pieces. So it's still like just making the set of numbers that we deal with just a little bit bigger. You know what I'm saying? Okay. So let's do some operations. So we'll do addition and subtraction first. And we'll just do some examples here because this is pretty easy to see what's going on. So let's say we're taking the complex number 7 plus 2i and adding to it the complex number 7 minus 3i. The way we add these together is we add the real parts together, 3 plus 7, and we add the imaginary parts together, 2 plus a negative 3, which is negative 1. Basically, all we're doing is we're treating that I like a variable and just combining like terms, right? So that's not a big deal. Let's do one more with subtraction. So with the subtraction, we have to be a little bit careful. What are we going to have to be a little bit careful about? Yeah, well, I got to make sure I distribute that negative throughout the entire second piece. So it's really plus 3 and then minus 4i. So when we combine our like terms, 3 plus 5 is 8, and negative 3 plus negative 4 is negative 7. But that's about as tricky as one of these addition or subtraction gets. No big deal, right? Okay. So let's look at multiplication. And again, we're just going to do some examples here. So let's say we just have 3 times 5 minus 2i. What does it look like we should do in this situation? Just distribute. Yep, that's all we're going to do. What if instead this was looked like this? Still distribute, right? So 4i times 3 is 12i, and 4i times 7i is 28i squared. But what does I squared mean? Just as a little aside, I squared would be, because I is the square root of negative 1, I squared would be the square root of negative 1 squared, right? Everybody's okay with that? Which the squared and square root cancel, so we get that I squared is negative 1. So this problem, I can replace that I squared with negative 1. And really this becomes negative 28 plus 12i. So this will be an important piece that we'll use a lot when we do multiplication, because we're going to get I squareds frequently, right, when we do multiplication. So far, so good? Okay. What if I have 1 or 2 minus 3i times 1 plus 4i? What do you suppose we want to do to multiply these out? What does it look like you would want to do? We want a FOIL, right? You have 2 sets of parentheses like this. Looks just like a FOIL problem. It's exactly what you'd want to do. So 2 times 1 is 2. 2 times 4i is 8i. Negative 3 times 1 is negative, or negative 3i times 1 is negative 3i. And then negative 3i times 4i is negative 12i squared. Now if I combine my like terms, 8i and negative 3i make 5i. And I know that I squared is negative 1. So really that's positive 12, and then the 2 makes 14 plus 5i. Everybody's okay there? Okay. We feel okay about multiplication. Those are basically the 3 situations you can run into, in which case you're either distributing or foiling. The only thing you have to kind of remember that is maybe something that's hard to forget or hard to remember is that I squared is negative 1, and we have to make sure that we get rid of all the I squareds, because our answer needs to be a complex number. So there should be no just an I and then just like a constant, right? So you can't have any I squareds or anything running around on you. Oops, I think we're at 3, not 4. Is division. So let's start with, well, I'm going to use this example that we did before. Actually, we'll write it. Yeah, that's fine. Keep in mind that we could have also written this that way. Right? Still the same problem. But we did this already. All we have to do is write this as, oops, that, right? No big deal. That's the simplest case. But if we have this, where we have an I now in the denominator, well, if our denominator has no real part, if it's just the imaginary part like we have here, where it's just a 5i, there's nothing added or subtracted from it, what we're going to do is we're just going to multiply the top and bottom by I. Let's see why that's going to be of help to us here in a second. So the I distributes in the numerator. And then it just multiplies into the denominator. And then we can replace all these I squareds with negative 1s. So I have 4 plus 3i over negative 5, which is now just like the previous problem, right? Is that okay? So again, we multiplied by I to the top and bottom of our fraction. And the result was a situation that was just like the first example. Great. Okay. Let's look at the trickiest of them. Let's say we have 2 minus 3i over 4 plus 2i. So first observation, multiplying the top and bottom by I is not going to be helpful for us. Because if we do that, we distribute the I through the denominator, and we're still going to have an I along with an I squared if we do that. So that's not going to be what we need. What we're going to do is we're going to multiply the top and bottom of this fraction by the conjugate of the denominator. So the conjugate is the same thing, just with the different sign in the middle. So we call these two things conjugates. Is the name we give to something like that. So they're the exact same thing. They're the same binomial piece, but they have a different sign in the middle, right? One is a plus, the other is a minus. Okay there? So now we're going to FOIL the numerator and denominator. So I have 8 minus 4i minus 12i plus 6i squared over 16 minus 8i plus 8i minus 4i squared. So far, so good with everybody? Okay. So let's combine the like terms and get rid of our I squareds. So negative 4i and negative 12i make negative 16i, and I squared is negative 1. Negative 8i and positive 8i give us 0. Fantastic. Minus 4. And then instead of I squared, we'll put a negative 1. So 6 times negative 1 is negative 6, plus 8 is 2. 16 minus a negative 4 is 20. And now we can just rewrite this as two fractions. And really, we should reduce those two fractions, right? 2 over 20 becomes 1 over 10. And 16 over 20 becomes 4 over 5. We okay there? Okay. The last operation that we want to worry about is absolute value. So to explain what we're about to do, we have to think about how we would arrange complex numbers on the number line. So think about this question, which is kind of a weird question. Let's say I have these two complex numbers. Which one is bigger? If I were going to put these on the number line, which one would come first? The question doesn't really make sense, right? There's no obvious way in which you'd want to do the ordering for this. That's because to really do this, we would need like a two-dimensional place to plot these numbers. Instead of just having a number line, a one-dimensional thing, where we can arrange them linearly, we need a two-dimensional space to arrange them. So we're going to put the real part on the x-axis and the imaginary part on the y-axis. So like 0 is here at the origin. And 3 plus 2i would be 3 over and 2 up. 2 plus 3i would be 2 over and 3 up. Everybody's okay with that notion? So instead of using a number line, we have to use like an xy plane. That's fine. If you remember back when we did absolute values, we defined the absolute value as the distance of that number to 0. So here, our absolute value is going to be the distance from that number to the origin. So if I think about it, say, for this piece, I can make like a right triangle where I went 3 over, 2 up. I don't think that's real. There's no shortened schedule today for anything. I think they're just trying to fool me. Anyway, so the distance there is the hypotenuse, right? That's the distance back to the origin. Everybody agree with that? So what that tells me then is the absolute value of a complex number, it's just going to be the length of the hypotenuse, so it's the square root of a squared plus b squared. So for example, if I did wanted the absolute value of 3 minus 4i, that's going to be 3 squared plus negative 4 squared, or 9 plus 16, which is 25, which is just 5. So all the absolute values are basically the same. You're just plugging them into that formula. No big deal. But that formula doesn't make a lick of sense unless we kind of describe geometrically what's going on, right? Is everybody okay with that? So no big deal there, right? Easy to do. You just use that formula every single time. And it's a formula we already know, right? Which is even better. You know, just the Pythagorean theorem. Yay! Right? Isn't it great when it's something that we've already know? Okay. So back to solving. So now, we can finally deal with situations like this. This looked identical to one of the situations we've seen before, right? In fact, I asked you to factor this in the homework. Well, I can do this now by using the quadratic formula. So negative b plus or minus square root b squared minus 4 times a times c all over 2 times a. 1 squared is just 1. 4 times 1 is 4. 1 minus 4 is negative 3. And this was a place where we ran into problems before, right? Until today, where we introduced the complex numbers, this would have been a problem. Everybody agree with that? We can fix that. So note that, actually, let's do it over here. Square root of negative 3 is the same thing as the square root of negative 1 times the square root of 3, right? Everybody okay with that notion? Remember when we talked about the properties of square roots last time? This was one of them that we used. And what's the square root of negative 1? That's I. So we're just going to write this answer as a complex number. And we're done. No big deal. How much time do we have left here? 10 minutes, huh? Do you guys want to program your calculator, or do you want to leave that for next time? We probably need to leave that for next time. It'll probably take more than 10 minutes to get everybody who's working. Let's do another example with a complex number thing coming up, okay? And then remind me next time we have to do our calculators. Or help me remember anyways. Okay. So first thing I would do here is add 6. Very good. Next I would divide by negative 2. So 6 divided by negative 2 is negative 3. And then next I would square root both sides. So remember, when we take the square root of both sides, it creates a plus or minus. And then we have a square root of a negative. So that's going to generate our I, square root 3, just like before. Everybody's okay with that? So a negative underneath the square root, you can just replace the negative with an I in front of the square root. And then the last step would be just to add the 4 over. And that's our final answer. Cool. Not much of a difference, right? Went through all that work to just put some I's in our answers. All right, well, that's kind of disappointing, Mr. Kulik, but that's what you get. Do we feel okay on this? Surely we'll do some more practice on solvings. So I'm going to give you, if you check back later today, I don't have the assignment ready, but if you check back at the end of the day, I'll have an assignment on OneNote in PowerSchool where I'm going to ask you to do some solvings. Some of the answers will get imaginary things, some of them won't. So I have sections where I ask you to solve with the quadratic formula, with a square root, and then I'll have a section where I ask you to solve whichever way you want, whether it's factoring or a square root or quadratic formula. Try to pick the easiest method. Some of the time you'll need to use I, some of the times you won't. And then I'll have some complex number operations in there too, adding, subtracting, multiplying, dividing, absolute value, to practice on those as well. Okay? Cool. Thank you, guys. We did a lot today. You should be proud. We're almost through with solving. We'll do a little bit more practice on this next week, and then we're on to graphing, and not too long before this chapter ends, but it won't be next week because we only have 2 days together next week, and certainly I can't finish it all in 2 days. That's unrealistic. But you can probably expect a homework quiz sometime next week with some factoring and solving questions on it. So if you wanted to get ready for that, that'll likely be what the content is on for that. Okay? Well, cool. Thank you, guys. You guys can relax here.